Hi everybody, Cal here with sections 1.3 and 1.4. 1.3 is on vector equations, and the first thing it's going to do is introduce vectors. We're going to be working with vectors all term, and so again you're going to want to get used to them now. The section starts out with vectors in R2. Now we'll be talking about R2, R3, Rn, and so on. R2 is all the space of two-dimensional vectors, vectors with two entries. R3 is the space of vectors with three entries. Rk is the space of vectors with k entries, and so on. We'll be playing with those quite a bit. So, bottom of 24 here starts talking about just basic vector arithmetic. It talks about what it means for two vectors to be equal. Moving forward, sum of two vectors, something called a scalar multiple of a vector by a number or scalar. And we're going to be using this terminology, all term, again. So you're going to want to understand what's the difference between a scalar and a vector. A scalar is just a real number. A vector is, well, a vector. Example 1 just gives a little bit of basic vector algebra. We get into geometric descriptions of R2 down in the bottom of 25 here, and we can identify vectors with, you want to think of them as rays coming from the origin in R2. If you've heard of vectors in a different context, you've heard of them as something with length and direction, and we will eventually reconcile this presentation with that one, but not until late in the course in Chapter 6. So be aware that the way you're seeing vectors here is different from the way that you've seen vectors before, and my apologies about the ringing. My dog is being a pain in the butt over here. Okay, so moving on. It talks about the parallelogram rule for addition, which helps the geometric intuition. You do want to pay attention to this stuff. We will be visualizing vectors quite a bit. So walk through example 2, example 3. These are getting at, what does addition look like? What do scalar multiples look like? That sort of thing. Vectors in R3, same thing, but we're dealing in 3 space. And vectors in Rn is more general. At the bottom of 27, we've got algebraic properties of Rn. How do adding and scalar multiplying and distributing vectors and all that stuff work? These are exactly what you would think that they would be once you kind of get used to how vectors work. This is the kind of thing, read it, you'll use it implicitly, but you don't need to memorize this block. All right. At the top of 28, we get into a big one. The idea of linear combinations is going to be one of the most important ideas in the course. You want to understand what linear combinations are. The idea of weights is just a terminology that's used in linear combinations. Example 4, this picture is pretty huge. Work through that. And keep going. Try to figure out example 5. This is all pretty solid, pretty basic stuff. The blurb at the top of 30 is going to be pretty important for us. We're going to be going back and forth between vector equations, augmented matrices, and linear systems. And we'll actually have a fourth notation coming up in a little bit. Okay, another definition here on 30, and this is again a really big one, the idea of span. It has to do with linear combinations. Make sure you know exactly how. You want to get down the ideas of span, the idea of linear combination really, really early. I will also say here, we are using the word span in 2 different senses. The first one, you can talk about the span of a set of vectors as a noun, the subset of Rn spanned by or generated by those vectors. We can also talk about a set of vectors spanning a certain space, and look out for that language. Span is a verb. You can look out for that language below. Starting at the bottom of 30, we get into a geometric description of the span of a set of vectors, and you do want to read that reasonably carefully. Work through example 6, certainly. We are going to put less emphasis on applications. I'll leave that to whatever classes in your own fields you're going to be using this stuff in for the most part. So example 7 might be nice and illustrative. You don't have to spend a lot of energy on it. Moving on to section 1.4, the matrix equation, AX equals B. So here we get into how to multiply a matrix by a vector. And the definition is going to be useful. It's definitely something you're going to want to be conversant with. It's not the usual way that we will think of matrix vector multiplication, though. You want to know this, but it's not going to be our go-to use of this concept. Do work through example 1 and 2. These are important. It's getting you used to this new notation. Here it introduces a matrix equation, which is going to be the fourth way of expressing a basic equation. So Theorem 3 kind of collects the different ways that we have of expressing systems of linear equations. There's a matrix equation, a vector equation, an augmented matrix, or just a naked system of linear equations. Here we get into existence of solutions on 37. And this is a pretty important blurb. This blurb really doesn't need to be pointed out if you're comfortable with your definitions, but getting comfortable with your definitions is the heart of this course. Example 3 illustrates how this can be used. Do work through that carefully. Theorem 4 is a biggie. Theorem 4 is one that you're actually going to need to memorize. And not just memorize, but again, understand why it works. If you can shuttle back and forth between the different language being used in A, B, and C, you'll understand that those three statements are literally the same statement. D is the how do we know. D is the meat of this. So A, B, and C are stating three different sounding properties that really are the same property if you unravel the language. And D tells us how you can tell when a matrix has that property. Theorem 4 is pretty huge, so just be aware. And take note of this warning. Theorem 4 is about a coefficient matrix, not an augmented matrix. The warning is pretty important. You should figure out why that is. Alright, finally, here on 38, we're going to get into how to actually compute a matrix vector product. So work through example 4, and you can kind of figure out what it's getting at here. How to actually compute the matrix vector product AX. It states it at the bottom here, but working through the examples 4 and 5 is going to be a little bit more valuable. We also introduce over here the identity matrix, I, which is going to be useful later on down the road. Then we get into algebraic properties of the matrix vector product AX, here on 39. Theorem 5 is going to be useful for reasons that aren't going to seem obvious yet. Take note of it now. It's not something I'm going to make you memorize. It'll come up again near the end of the chapter. And that's really about it for this section. So, there you have it.